Hi, I'm Ed, and today I'm presenting my work on a flexible high-level abstraction for topography implementation within finite difference wave solvers. Finite difference methods are at the core of many seismic modeling and processing applications, including migration and full waveform inversion. So accurately solving wave equations in the presence of complex topography, as we may have to do when dealing with land seismic data, for example, presents a challenge as the free surface is unlikely to be aligned with the structured grid. So approximating a boundary to the grid results in errors due to staircasing, and if we're using something like an air layer formulation, we will also have errors stemming from the non-differentiable nature of the field across that interface. So ideally, we would prefer to have a curvilinear free surface boundary representing our topography. However, this is going to require more sophisticated modifications to the numerical scheme, which in turn are going to complicate the solver, and this translates to more time to implement the solver, which is going to be particularly egregious given that most immersed boundary schemes are single purpose. So as such, we are presenting a high-level abstraction for immersed boundary specification, and we will show a benchmark against a conventional free surface, along with a wave field model in mountainous terrain, and demonstrate that they produce realistic results. So why might we need an abstraction for the curvilinear topography problem? So whilst we have numerous related problems with several wave equation formulations, etc., and each of these is going to require its own boundary scheme, all of them are going to have fairly similar underpinnings, which means that we can either reuse components or modify them slightly to suit differing specifications. And as such, it makes sense to essentially provide some kind of abstraction for this problem, which DeVito Boundary does by leveraging symbolic computation to automatically generate schemes to suit user requirements. So over the past couple of slides, I have mentioned immersed boundaries. And what are these? So immersed boundaries are essentially a means of implementing surfaces of arbitrary shape within finite difference schemes. So if we consider our standard boundary condition implementation, so for like Dirichlet, Neumann conditions, etc., in finite difference schemes, we can generally think of these as an extrapolation of some form around a grid node. So we can generalize this to non-node locations, which enables the representation of curvilinear topography on regular grids. So if we create an appropriate extrapolation which obeys our boundary conditions on the curvilinear surface, then it allows our interior solution to essentially be extrapolated to exterior points. And doing this avoids the need for sort of geometric transformations, so curvilinear grids, to essentially warp the finite difference grid such that it conforms with the topography, which simplifies things somewhat. So the immersed boundary scheme used by DeVito Boundary is a generalization of that detailed in Mulder's 2017 paper. So it uses symbolic computation to automatically determine extrapolations from boundary conditions and discretization. So Mulder-type schemes differ from other approaches in two key ways, the first of which is the use of independent extrapolation schemes for each Cartesian direction, as opposed to a single extrapolation perpendicular to the boundary, thereby avoiding potentially instability-inducing ambiguities. So the second key difference is that the boundary is encapsulated through modified stencil coefficients, which negates the need for ghost nodes, and also enables straightforward local modification for stability in areas where the boundary is tightly curved. So whilst the idea of representing a boundary through modified stencils might be unintuitive at first, essentially we can think of it as creating a single stencil which represents the application of a derivative to a partially extrapolated function. So to help explain the process by which DeVito Boundary derives modifications to boundary intersecting stencils, we will consider a derivative stencil of space odd 4 intersecting a boundary at xb. So our function u of x is approximated beyond the last interior node using a polynomial of equivalent order to the stencil. And if we substitute this polynomial into the boundary conditions imposed on the surface and carry out additional polynomial expansions at arbitrary positions, we can produce a square system of linear equations, which we can then solve to get the coefficients of our extrapolation polynomial as which will obey our boundary conditions at xb, and these coefficients will be in terms of our arbitrary positions, the function values at those points, and eta, so our distance to the boundary. So the aforementioned arbitrary points in our extrapolation polynomial can then be replaced with interior stencil points, the choice of which is dependent upon eta. So as you may have noticed, including points which lie close to the boundary in the extrapolation may result in an excessively rough function, which will lead to instability. So to deal with that, a rule is introduced saying that points lying closer than half a grid spacing from the boundary are excluded from the extrapolation. So the extrapolation polynomial, once we have our stencil points chosen, our interior stencil points chosen, we can then evaluate our extrapolation polynomial at the exterior points, and these values can be substituted into the derivative stencil, thus eliminating those points from the stencil. And the resulting stencil coefficients are now a function of eta, so we essentially have stencils that are dependent on their distance to the boundary. So this approach is reasonably straightforward to extend to higher order discretizations or a large suite of boundary conditions. So where stencils intersect the boundary at both ends, two independent extrapolations are applied, or where necessary, a unified polynomial of higher order may need to be formed. And for any combination of boundary conditions, discretization, and derivative, there are order plus 1 squared stencil variants, which each represent a combination of differing degrees of truncation at each end of the stencil. So once this set of stencil variants for the problem is calculated, stencils can essentially just be selected and evaluated as needed. So we will now zoom out to take a look at the DeVita boundary pipeline and its interface with DeVita. So on the left, the user is going to provide a surface file, a list of boundary conditions, and a set of derivatives required by the equations. So stencils are generated through the previously detailed method, and axial distances, so eta, so the boundary at grid nodes adjacent to the surface, are stored. And with these, essentially all the points within the area of effect of the boundary can be identified, and stencils can be generated for these points. So the set of modified stencils is then passed to DeVito as one will pass any other set of custom stencil coefficients. So for example, if you wanted to have like a dispersion relation preserving scheme, for example. So from here on out, the standard DeVito workflow applies. So as you may have observed on the previous slide, stencil generation is entirely limited to the pre-processing step. As such, modified coefficients for a problem can be cached and reused in multiple models or runs. So whilst DeVito boundary itself is currently only single thread, there are plans to make use of MPI, Dask, or some combination thereof to achieve speed up for larger applications. So for DeVito, I mean, it produces very highly optimized, parallelized low-level code. So you're going to get the same high performance you always would there. However, we do need to make some performance optimizations to DeVito boundary before we can make meaningful comparisons between models which have immersed boundaries and models which do not. So to validate the boundary surfaces generated by DeVito boundary, we will take a model cube, so 1.2 kilometers across with a grid spacing of 10 meters. So we're going to cut this in half along the y-axis, and we can see that we have absorbing layers on all sides, and we have 10 absorbing layers in this setup. So within this domain, we are going to implement a free surface boundary by conventional means, so essentially mirroring points at nodes on either side of the boundary and forcing 0 at the boundary nodes. So below this, we're going to have an array of 101 receivers and a single Ricca source below that. So if we take this setup and replace the conventional free surface with an immersed boundary, we are able to essentially rotate this whole boundary source receiver's assembly around the center of the cross section. So as the relative geometry, when we do this, is not changing, even though the setup is now at an angle to the grid, we should expect to see the same results in the shot gather. So walking through these gathers, so for 5 degrees, 10 degrees, 15, 20, 25, 30, 35, 40, and 45 degrees, we see that misfits between the original tilted examples are fairly small, to the point where they are essentially indistinguishable by visual inspection. So taking the difference reveals that the misfits in the direct wave are of similar magnitude to those in the reflected, which implies that any differences induced by the immersed boundary treatment are essentially eclipsed by differences in interpolation of source and receiver terms. So on to a slightly more exciting example. So we have here on the left a DEM of a mountainous area of Oregon. So this is taken from the SRTM dataset. And this is very mountainous terrain with about 700 meters of elevation variation, and is the sort of complex surface geometry that most wave solvers would struggle to handle. So we will now briefly go over our model configuration. So we have a 10.8 by 10.8 by 5.4 kilometer grid with 50 meter spacing and a homogeneous p-wave velocity of 1.2 kilometers per second. So this is of note since any reflections that you see are products of the immersed boundary and not of any sort of contrast in material properties. So our finite difference scheme is fourth order in space, second in time, and we are imposing a free surface on this surface shown embedded in the model cube. So we also have a Ricca source positioned centrally 500 meters below sea level. And if we run this, we get the following result. As we can see, we get a very complex, albeit realistic pattern of reflections from the interaction between the wave and the topography. And as we move to the next slide, we can see a short animation of this wave propagating, and once again we can see this realistic pattern of reflection, and also we can see that there is no leakage through the boundary, implying that the free surface treatment is working as intended. To summarize, when using immersed boundaries to implement topography in seismic wave modeling applications, high-level abstractions and symbolic computation enable a high degree of generality. Furthermore, using a simple immersed boundary scheme, which is implemented in terms of variable stencil coefficients, enables a flexible, stable, and accurate boundary representation. So finally, we showed a validation and a test case using this scheme, and both demonstrate expected wave field behavior in the presence of non-grid aligned topography. Thank you for listening.